welcome everyone to this week's Autonomy Talk. This week is an honor to have with us Professor Naira Hovakimyan, who is a friend, and I'm very excited to have her because she's a great powerhouse in the community. So I want to attempt before the talk to give an introduction to Naira, although it's quite hard, right? If you have seen her bio, I could spend the next hour essentially talking about what she has done. But I will try to essentially highlight some things. So first of all, Naira is the W. Grafton and Lilia B. Wilkins Professors of Mechanical Science and Engineering and the director of the Aviate Center at the University of Illinois at Urbana-Champaign. She received her Master of Science in Applied Mathematics from Yerevan State University in Armenia, and then her PhD in Physics and Mathematics from the Institute of Applied Mathematics of the Russian Academy of Sciences in Moscow. So I want to highlight two things. Naira is, first of all, a great researcher, but also an amazing mentor and community builder. So from the perspective of research, if you look at her record, it kind of speaks by itself, right? She's written books, she has 11 patents, she wrote over 500 papers. And so if you see, she has been working on all sorts of things from control, optimization, autonomy, and machine learning with transformative applications from aerospace and robotics to agriculture and even elderly care. And all these efforts have been awarded a big number of awards, from the Control System Society Award for Technical Excellence in Aerospace Controls, but also the Humboldt Prize for Lifetime Achievements. The second trait I want to highlight is that she's also a mentor and a community builder. That's also the way I met her. Like she's been a mentor to me, and her impact is incredible. And this is not only me saying this. UIUC awarded her twice the Engineering Council Award for Excellence in Advising, and recently she also got the Excellence in Graduate Student Mentoring. And, she's not only an academic, she has co-founded and is a chief scientist for a company named Interlinear, and her work has appeared everywhere in many news sources. So today, Naira will delight us with a talk on robust learning for autonomy architectures, which is a topic which I really like, and I want to dig deeper in that. Feel free to ask questions in the chat or to raise your hand during the talk. But without further ado, I want to give most of the time to Naira. Thanks so much for coming today, and I look forward to the talk.
Thank you, Giole. It's an honor for me to be here, and I want to thank all the participants who are taking this hour from their busy day to attend this talk. So let's get started. So like Giole presented, my background was in mathematics, applied mathematics. And when in 1998 I landed in Georgia Tech, the community, the department, and our particular group, and Dr. Cleese, my former mentor, is here on this talk, we were working on the big, highly profitable, large-scale, powerful systems and attempting to achieve adaptive flight control for these systems in the presence of uncertainties. Over the past 20 years, 25 years actually and more, as I worked in this country, the industry shifted more towards autonomous systems, low-cost platforms, multi-agent configurations, human-centered architectures. And this shift in the industry, as we observed, as it happened in front of our eyes, was largely conditioned by the fact that the GPU, CPU technologies became cheap and available, which boosted the machine learning algorithms up to foundation models, large language models. But from the perspective of aerospace industry, what we observed that from high altitude space, we went to low altitude space to do parcel delivery, emergency response, spraying for farms, and other types of applications that are typical for low altitude operations. So as we summarize this observation, so if we look into commercial aviation's evolution over the past century, it has been already more than 100 years that we have commercial aviation available to us. By enforcing zero tolerance to accidents, the commercial aviation has achieved safety and public trust by traveling 4.5 billion passengers over the year. And this is undoubtedly one of the safest industries for transportation. As we now move into low altitude space, we need to kind of develop the same level of public trust, because what we observe, especially over the last year, starting from this near DCA airport collision and many other accidents that happen in the low altitude space have to do with the fact that this industry for the low altitude space is not yet ready, is not yet mature. And here there are lots of issues to be solved, from path planning, routing, optimization, autonomy, and other types of solutions that can be vital for improving the safety for this low altitude space. So this is one example scenario that was put up by MIT and Lockheed Martin back in 2018 to address, for example, challenges that have to do with emergency response in post-disaster areas. And what we observe in this environment, that one has basically to have vision-based sensors that can map the environment, help you to navigate the vehicle. And in this environment, we need to have all types of guarantees of safety, robustness, robust learning in this environment, fast path replanning, things that we do not have to deal with, for example, in commercial aviation, when your flight envelope is prefixed, predetermined, and there are maybe minor modifications along the way as you go. Here we have continuous update of the environmental map that decides your next navigation point, and it brings up new challenges for the control design solutions. So what is the situation here for the autonomy pipeline that we are interested in improving? So we have sensors that map the environment. The sensors help the planner to generate a path, and then the autopilot has to develop it, right? So if we go forward, so the sensors map the environment, identifying obstacles, hazards, and goals. The planner generates the trajectories that the low-level autopilot has to follow this path. So the key questions that arise here: what if the autopilot cannot deliver what the planner is asking for? And what if the planner does not account for the errors in the environmental map? So it's critical that the autopilot has awareness of its own performance and limits, and it's capable of communicating it back to the planner so that they can work in coordination, right? This is basically the autonomy challenge. You have sensors, and you have basically to execute what the sensors map and guarantee as safety in terms of a planning trajectory, and then you have to get back. So the fundamental challenge here that exists is the language barrier, because these are different systems on different levels of abstraction, and they need all to talk the same language. So because we have subsystems with data-driven learned components, while the typical autopilot will have, say, PID controller or some other controller that comes from some deterministic model. And this language barrier creates lots of challenges in terms of assessing the system's performance and robustness. So the questions that we are facing: what should the components communicate in between each other? And what should be the language for the communication? Typically, because this whole pipeline is huge, it goes from this mapping, sensing, planning, up to control. We observe different communities talking, developing their results in their own language, and quite often they don't talk to each other in a proficient way. For example, people who do computer vision, who do path planning, they always make an assumption that there is some good autopilot that can track and follow whatever they do. But this may not be the case always, and this is where sometimes the robustness challenges appear. So general consolidation between machine learning and control should solve this language barrier problem. So given a system, one would try to create its estimate by using the data and considering some model class, let it be neural networks, and minimizing a loss function, which would be kind of the mathematical expectation of the loss function over the training data that was available to build this estimated model I've had. We refer to it like empirical risk. So it depends upon this empirical data distribution that's given to you, either available from past experiments, past trials, or simulations, flight simulators. There is some empirical data. There is a model class that we would choose, and based on that, we will minimize this mathematical expectation over the training data, referring to it like empirical risk. What guarantees we can expect from these machine learned models? The trained model usually will give us the parametric estimate, right? And the learned model certificate, to which we will refer like model risk, it will be guaranteed, it will be dependent upon the distributions. These are distribution dependent performance guarantees. It can be extended to Wasserstein ambiguity sets around the empirical distributions, and the literature is rich with different tools how to achieve it. So, however, when we go to the real world, we would rarely experience the same data sets, right? So there will be always data that has not been captured during the training, during this machine learning process. So the causes of these distribution shifts are insufficient data, which can be epistemic, these are the learnable data, and aleatoric, which are unlearnable, the disturbances, the environmental uncertainties, which cannot be predicted. Engineers like to refer to these like known unknowns, unknown unknowns. In machine learning community, they refer to it like epistemic and aleatoric uncertainties. So what are the typical solutions? So these uncertainties that, for example, the part of it that could be learned, one class of uncertainties have an acceptable cost. For example, if you look into these animations on the right, you can infinitely play with it, crash, fail, collect the data, learn again, and kind of make sure that your machine learning model gets better and better with more data and more learning. But when we deal with safety critical systems like airplanes or landing a rover on Mars, you cannot go and crash infinite times, learn, collect the data, crash, and get this perfect machine learned model. So the cost here is prohibitive, because we need, in these cases, we need other methods to ensure safety without going through this prohibitive cost. We need to analyze the systems that generate the data. We need to have architectures that would ensure safety regardless of the performance of the learning. This is the key point. So how can we ensure predictable and safe use of machine learning methods in controls? The guarantees that are defined distributionally, they are not on finite dimensional vector spaces, but probability measures on them. Therefore, we need control architectures that would satisfy a priori uniform guarantees on the space of distributions, probability measures, and they would be applicable to general class of nonlinear systems, subject to both epistemic and aleatoric uncertainties. This way, we can enable safe use of machine learning in control, right? And we can have safe predictive control, so to say. Integrating both, like a control architecture that would have these a priori guarantees, that would enable accommodation of a machine learning model, should be cast in a way so that it kind of boosts our natural ability to consider epistemic and aleatoric uncertainties, the models of which are typically stochastic. And we can bridge the space between the design space and the test space. If you look now today, for example, the way the commercial aviation flight controllers are certified, they are designed deterministically using some gain scheduling, linearization, PIDs or LQRs with robust augmentation, and then they are being tested in Monte Carlo simulations where uncertainties are inserted that are of stochastic nature. And then if you check all the Monte Carlo green, you are good to go. But we can have a rigorous connection between the two spaces if we talk the same language and provide mathematical foundations, rigorous proofs to merge the language between the two spaces to have everything kind of provable and predictable. The field of distributional robust control is rich. We are not the first ones asking questions of this nature, and we borrow lots of the results from the existing literature. However, there is one fundamental difference between what we do and what others do, and I will go through the details through the presentation. We do not implement distributional feedback. We will prove distributional robustness guarantees for a deterministic feedback, and I will clarify this difference through my presentation. So assume you have some machine learned model, which is here the f hat, kind of subindex with theta, function of system states and controls, that has given you the optimal control policy, denoted here by pi star. And as we implement, so we face this distribution shift because the data in the real world will be different from the one that was used during training. And we augment the system basically here. We want to augment it basically with our L1 adaptive controller that has been flown and tested on numerous systems over the past 20 years. So why L1 adaptive control? And it's a deterministic controller, but here is where we work to make sure the language is clean and all the proofs are very rigorous when you bring in a deterministic controller into a machine learned architecture kind of. So let me just do a brief recap of L1 adaptive controller. I have presented for MIT twice, so I will repeat a few things which are important for the rest of this presentation. It's an adaptive control architecture that has a low-pass filter in it. However, the low-pass filter is not blindly inserted into conventional model reference adaptive controllers. Before insertion of it, we use a state predictor type architecture to have a well-conditioned error dynamics, which is agnostic to the control signal and allows this low-pass filter insertion very rigorously. It helps us to decouple the performance bounds based on the adaptation gain, which improves the performance. The faster you adapt, the better you do. And the robustness is tuned through the bandwidth of this low-pass filter. This decoupling of adaptation and performance is the key to the successful deployment of L1 adaptive controllers across a various range of platforms. So this architecture relies on small gain theorem and Lyapunov stability theory for its proofs. And these methods are well established and exercised over the years. This is a deterministic solution, so it has certain conservatism coming from small gain theorem and Lyapunov stability theory. The history of L1 adaptive control is summarized in this slide, starting from 2006, when we had the first papers appearing in ACC. In the same year, we had a path planning paper with a flight test appearing in AIAA GNC conference. The flights were done by Naval Postgraduate School using the Rascal autopilot, Rascal UAV with Piccolo autopilot. Then during 2007 to 10, we had NASA flight testing the L1 adaptive controller on a subscale Boeing 757 model that you see here on this slide. Later, this success story led us to lots of opportunities to work with Raytheon, Boeing, and other companies like Eurocopter, MBDA, for testing it on different platforms. Raymarine commercialized it for evolution autopilots for marine vehicles. Caterpillar commercialized it for hydraulic pumps. Statoil tested it on experimental rig, and then that was before the oil prices crashed, and we remained on the experimental rig. It didn't move forward due to the change of the world towards green technologies. So kind of there was a period when the oil industry was suffering. Later, we got this opportunity from 2018 to 20 to test it on real Learjet and the Vista F-16 platforms at Edwards Air Force Base. Test pilot school. I had a former student working there who kind of gave us the opportunity to fly these platforms, and I will show some movies now. Starting 2020, we moved into this safe learning and control, because in 2018, that's when I visited Georgia Tech, and Evangelos Theodorou challenged me if we could bring it to these drone racing environments. And it was clear that in a drone racing environment, we don't have the luxury of a flight envelope given to us. It is being continuously updated, which means that we need new types of solutions and new types of guarantees. And last year already, Lockheed Martin, as a part of ONR SAFE program and our NASA ULI project, they were our industrial partners, they transferred it to the Vista X62 model at again Edwards Air Force Base, where we have the modernized platform suitable for autonomy architectures. And they claimed TRL6. Claiming TRL6 at a major industry is a big deal, especially when you touch the inner loop controller. Going through this was really a proud moment for us. So here are some brief flight tests from NASA past 2007-10. So when NASA spent a few years to build this subscale Boeing 757 model, and they pushed it into stall and post-stall. These are one of the first tests here. As you see here is where they go into stall condition. The airspeed drops below 40. I have a small movie here to show how that thing works. You will see the pilots.
Hour. Slow down just a little bit. Zoom too much. We're going to try ramping up to 15. Okay. Hold it around 18. Okay. Slow back to normal flight. You ready?
Yep,
Normal flight.
yep,
Okay.
yep.
Right there now.
Okay. Fuel state is 4.7. Let's repeat that. Climb maintain 1,200.
And the reason they repeat is to test the transient performance bounds, because this is our major claim.
Now, slow down a little bit. Okay, gonna start my pull here. Okay. Bingo.
They ran out of gas.
Cover.
So just to summarize, this was the only controller flown by NASA into stall and post-stall flight regimes. Here is where they go into the departure edge of the flight envelope. The stall occurs at 12-degree angle of attack, as you see, and they push it to 28, and they start Schroeder sweeps for system identification.
Setting 40% RPM for the entry.
Okay, so they use it for updating the aerodynamic models. Here is a quick capture of that two trials of going into stall and post-stall, and they even say repeated oscillations, like, because when they go through that stall condition there is some shaking. So the repeatable results were verified per the theory. And it's more exciting, of course, to watch how it was flown on manned aircraft, because it's one thing unmanned, it's one thing manned. With the manned aircraft, they didn't have the flight opportunity to go into stall and post-stall. But here is a flight test when the pilots are required to do flying qualities assessment. So when you fly an airplane and you have no fasten seatbelt sign, it's flying qualities level 1. When you get a little bit turbulence, then it drops to flying qualities level 2, level 3. So the test pilot school students who are going to get pilot license are given this paper that has the scale, the Cooper-Harper rating scale, and they have to do flying qualities evaluation. And when the airplane shakes up because of the disturbance inserted, and this was the type of F-100 Sabre dance, there is such a famous accident, I don't show it here now. So they are asked to do this flying qualities evaluation, and it's very shaky, they can't do it. They ask for the L1 controller to come on. So you will see they request Cooper-Harper ratings, CHR ratings. It will come up as an abbreviation. I give the preview so that you know what to watch for.
Constantly overshoot my desired bank though. Jason's probably hating life right now.
You're going around 27. I'd recommend you just do the cast with L1 on and once you're both pressed.
Got it. All right,
That's enough time.
you did not get adequate on that one?
Okay.
Okay, so if you want to run through a CHR real quick, you did not get adequate. So we're starting in.
Can I get L1 on as we do the
Yep. On in 3, 2, 1. Now Ellen is on.
Thank you. If you didn't ask, I was gonna.
And now they go for landing. This is something that NASA didn't do, like because landing is considered challenging. So Air Force does not go into stall, NASA does not go into landing. We explore whatever we can on whatever platform is available to us.
200 feet. 100 feet. 50 feet. Shallow. Looking good. The ground effect, you see that? Uneventful to me. Very uneventful.
So this is the key with the landing. And then we had more flight tests. So we were on some media cover sheets. We had also this Vista F-16 platform, which we were not allowed, I believe, by then to show, although now Lockheed Martin flew the same vehicle. In 2018, we went for different types of uncertainties. And in this case, they had an aircraft accident data from 1967 that they were able to load on the airplane and to see how the airplane will behave without our controller and with our controller. So this is the way the pilots get their pilot license. They have this test aircraft on which they can mimic different dynamics by loading data from past accidents or mimicking other conditions. And it has this various variable stability system that can shut down the accident to save the aircraft. Like now you will see, it's a second and it shut down the accident so that to save the airplane.
I can't even control the airplane. Do you have your airplane?
You see, the student on the left is my student, and on the right we have the flight test engineer. Now L1 controller on, they go through the same accident.
Okay, task in 3, 2, 1. Now? So you can feel there in high frequency, I made some high frequency inputs, excited the roll. Lower frequency, the roll, overshoot, or oscillation tendency is less.
Sounds good.
There's still some there. Pitch, I'm having no issues. Fine tracking and gross tracking are very good at pitch.
All right, and I have maneuver complete.
You listened, it said there is still something there, and our stochastic analysis brings the answer to that. Now they go into engine out flight test.
All right, recording on in ready, hack.
Running. Okay, power's coming back. My hands are free. 3, 2, 1, now. Controls fixed. Recover, please.
You see 20-degree bank degradation here on the right.
I'm ready to try this now with with a pilot correcting for it. So
Okay, I'll give it about 1 second reaction time. I am on conditions.
all right, and then recording on my call. Ready, hack.
On. Okay, power will be left throttle. Okay, in 3, 2, 1, now. 1 potato and recovery.
And recording off.
Okay, recording off, matching throttle.
And now they go with L1.
Ready for the recording on ready, hack.
On. Okay, left throttle coming back in 3, 2, 1, now. I'm not touching the controls. Nice demonstration. Yeah, check that out. About 3 degrees of left bank. Speeding in the rudder to match. I can feel it. It is descending a little bit, but it's descending a bit, but that would be easy to compensate for. Yeah. Okay. I think you got some good data there.
All right, recording off.
Matching power, recordings coming off.
So you see something was left there in the first flight and something like 3 degrees are left here in case of engine shutdown. And these are questions that the deterministic analysis could not answer, but the stochastic analysis that we did brought the answer for these questions. And now I will go through details. We were on the front page of Aerospace Defense Technology. I got this message from our College of Engineering. I was not interviewed in this case. It was great to see that we were captured by some media sources, while in the previous cases we were interviewed always by Aviation Week. So with these great success stories, so this year we had already Lockheed Martin using the modernized Vista for autonomy architectures, flying hit-to guns with a failed right flap. I have only 12 seconds of video released by Lockheed Martin for my presentations. Just observe how it remains in green, and in the other case, without L1, it's out of the green. So SAFE refers to ONR SAFE program, and Lockheed Martin was able to claim here TRL6, Technology Readiness Level 6. We had other applications of L1 adaptive controller to different other platforms, like, for example, this is what got us into New York Times. I'll just show it was for elderly care, something out of fantasy. But it was fun to work with psychologists who help to build anxiety models that can be used in the path planning cost functions and enable such different indoor applications. And we use VR systems to test people's perception of safety. And fantasy, because we kind of watch this Disney cartoon to kind of formulate some problems, right? So here is, they try to shower. So you see lots of control problems come up. Basically coming to this environment now, what motivated this presentation. So we have to formulate kind of the problems, understand what's the challenge, unpredictable environments, obstacle reach. This is not the open flight envelope, 30,000 feet high without obstacles, where you just have to do path planning and that's it. And then you just deal with weather uncertainties or kind of disturbances from the climate changes. Here you have to do fast replanning, continuously map your environment. It's an emergency response situation. And what does this mean? This means that if in the context of L1 adaptive controls, deterministic development, we had paid attention to transient performance guarantee, steady state performance, time delay margin, disturbance rejection, the basics of 101 controls that we teach on junior level or senior level control class on classical control. So now as the world around it changes, we need new forms of guarantees. We need guarantees that would work with stochastic planners. The stochastic planner is giving me a reference path, which I do not know a priori. It continuously updates. So this means that the conventional classical control deterministic guarantees are not good for these environments. We need new type of distributional guarantees. And I was challenged to look into this environment during my 2018 visit to Georgia Tech by Evangelos Theodorou, who was one of the finalists of that competition. And he used the MPPI controller, although he did not come out as the finalist, as the winner, but he was one of the finalists. He was well familiar with the environment. And he uses this model predictive path integral controller that provides a framework for solving nonlinear MPC with complex constraints in near real time. And he asked us if we could bring L1 adaptive controller as an augmentation to it. So we have a nonlinear system with known and unknown components where he applies the MPPI. It helps to update the control sequence iteratively by sampling thousands of trajectories. And we bring L1 to robustify against the discrepancies. So this type of architecture can help to leverage parallel sampling for modern GPUs and can handle complex, possibly non-differentiable dynamics and cost functions. This was an empirical trial, and we were able to clean all the gates that he failed to clean. We got a paper in 2020 IROS, and I have to acknowledge all the students of Georgia Tech that tirelessly worked. You know, 2020, that was the COVID year, and doing these trials at Georgia Tech, the students had to go into the lab in turns with masks and make this happen. And we made it. So it took us a bit longer, maybe, if otherwise we had the opportunity to work together closely, send our students to Georgia Tech, get them back. But doing everything remotely, going into lab one by one, and testing it was really challenging. And they have some flight test also with at Georgia Tech, the movie which I do not have. So this experience led us to formulating L1 adaptive augmentation, also a model-based reinforcement learning algorithm. So we're augmenting now machine learning baseline controllers. That was MPPI. Now trying to augment a model-based reinforcement learning algorithm. So we have new challenges. So these reinforcement learning algorithms learn models that are highly nonlinear, and the parameters of it do not equal the true parameters of the physical system. Nominal models produced by MBRL are not amenable to control tools. The one possible solution is to constrain the model structure to the control of fine or linear class at the price of sacrificing the performance. So we have to bring in L1 as an add-on module for an existing MBRL algorithm. And here are the design requirements that we have to acknowledge and face. So one is that the high-level MBRL cannot be changed, and no additional requirements from the high-level MBRL can be made. So we have to integrate an MBRL baseline model with L1 adaptive controller when L1 is operated on the need of affinizing the learned dynamics, and affinization happens along the control trajectories, and L1 gets implemented on the defined dynamics. We got the paper into ICLR 2024. It was presented by my students in Vienna during this conference. And we tested the 5 benchmark environments for MBRL: inverted pendulum, swimmer, hopper, walker, and half cheetah. So we got that in all the cases, except for one, L1 adaptive augmentation improved the performance of MBRL when tested for new environments, the data of which was not used during training. This is the challenge. MBRL was well trained, well working. You put it into a new environment, it has performance deterioration. And almost in every case, we improve the performance with L1, and this is a single L1 design for all these environments without redesign or retuning. That's why, for example, in one of the cases, we did not have improvement. So now our guarantees are probabilistic. And while these two papers, as I mentioned, that MPPI from IROS and this one from ICLR, were done empirically largely, we developed the rigorous theory since then, having this empirical evidence for distributionally robust guarantees. So let's look into a nonlinear Ito process where we have the uncertain drift term that can be decomposed into known and unknown components. And we have uncertain diffusion term, which can also be decomposed into known and unknown components. And we have the Brownian motion for modeling the aleatoric uncertainty. As the true system evolves, so we can rewrite now these terms, the known and unknown diffusion, known and unknown drift terms, and we have to build a nominal system for our analysis. As always, we need a nominal system, some baseline with respect to which our adaptive augmentation will compensate for the uncertainties. The nominal system to be built here is using the known terms of the drift and diffusion and is using a nominal Brownian motion. So the nominal system is free of epistemic uncertainties, but it cannot be free from aleatoric uncertainties, the Brownian motion, because otherwise it's not a fair nominal system for a nonlinear Ito process. But the key assumption that one has to make here and face is that the Brownian motions of the true system and the nominal system have to be independent. This is a very challenging assumption, and this is what helps us to justify those small disturbances that the pilots complained. There is something still left there. There is 3 degrees left, but that was good enough. And it is this independence of the Brownian motions that justifies these deviations that we observe in real world. Otherwise, saying in real world, there is always some noise which can never be captured. And this analysis brings up. So there is a distribution shift, obviously, between the nominal system and the true system. So now, what is our goal? Our goal is to design a feedback augmentation such that the true distribution remains uniformly bounded around the nominal distribution, and the robustness bounds can be used for upstream distributionally robust planning and control, and the bounds will consider in Wasserstein metric, which we borrow from optimal transport theory, a metric that deserves the distance and shape on the space of the distributions. Moving forward, we need some assumptions on the nominal system. If this is our nominal system, if we take out the diffusion term and are left with drift, it's a nominal deterministic subsystem. Let's first formulate the assumptions for it. For the nominal deterministic subsystem, our optimized control policy must ensure incremental exponential stability and existence of incremental Lyapunov functions that would help us to do this proof. So this analysis is done using incremental Lyapunov functions, matrix measures, Finsler-Lyapunov functions, and Riemannian metric conditions. For details, there are a bunch of papers. So this type of analysis is important to have at place for the nominal deterministic subsystem in the absence of the diffusion term, which also takes away the Brownian motion, the aleatoric uncertainty. Now looking into the nominal system and the true system, here is our L1 adaptive control architecture that would come as an augmentation to that baseline policy and to improve its performance against the new data not used in the training. The controller has three main components. It's the state predictor that conditions the aerodynamics, adaptation law, and the low pass filter. So moving forward, here are the elements of the controller. So it retains the identical structure of the deterministic controller. It's a standard implementation. Stochasticity is inherited through feedback. There is colored noise feedback injection because XT, the true system process, is driven by WT, by the Brownian motion. So we have the deterministic controller that was flown on this Learjet, Vista, subscale Boeing 757. And we look into the analysis of this controller when it's working in the true system, in the real world. When it works in the real world, so the stochasticity comes through the feedback. So it's important to correctly understand, we are not implementing a distributional feedback. We are implementing the deterministic feedback. There is no unreasonable assumption here that we are running a distributional L1 adaptive controller, running million samples, picking one at every second. No, it's the deterministic controller that's flying. We're trying to get guarantees for it in the space of distributions. And that implies we need to understand that the deterministic controller, when it's implemented, it inherits colored noise through the injection of the state and the Brownian motion. Through the feedback loops, it gets all kinds of bad things that make the process very hard. That's why finalizing this paper took 4 years from us, because we didn't want to step away from what's happening in the real world to make our life in mathematical proofs easier. We wanted to prove what's the real, right? So the real thing. So now we look into the different elements. The state predictor mimics the system structure, replacing the uncertainties by its estimates that you see here. So the components rely on deterministic, non-deterministic subsystem, state feedback injection, adaptive estimates. The deterministic dynamics is basically driven by colored noise injection. So colored noise input comes through the state because it's measured by sensors that would bring all the junk. And there is no access to the driving Brownian motion. This is the key. There is no access to it. That's why the best estimate of it is 0. So we form the error dynamics. It gives us the learning signal. It's driven by stochastic estimation error. The estimation error includes the drift uncertainty plus the complete diffusion vector field. It cannot disambiguate between epistemic and aleatoric uncertainties. So this is the mean error, and this is error standard deviation. And the quadratic variation of the Brownian motion helps us to get some type of new bounds that we do not have in deterministic case. So the adaptation laws, we use the piecewise constant learning signal. These are new type of adaptive laws that were derived in the process of development of L1 adaptive control theory. This is not the projection based. This is not the gradient descent. These are new types of estimation laws. They are piecewise constant. The sampling period is TS. The estimation error here can be again evaluated. You see the square root here for the standard deviation. And we have the kind of piecewise constant adaptive law summarized here. The adaptive estimate's accuracy improves as the sampling interval goes to 0. This quantity phi, it's the state transition matrix in deterministic case, so it's computed before runtime. And minimal computation is needed to produce adaptive estimates. These are all linear operations. It's numerically stable, avoids stiffness. And the control law is a low-pass filter. Here we particularly did this proof for first-order filter, but it can be generalized to arbitrary order. It's absolutely continuous for adaptive estimates driven by strong solutions. It's first-order low-pass filter with bandwidth omega. And this is the matched component of the adaptive estimate. We get uniform bounds guaranteed in the space of distributions and also pathwise. So what do these bounds say? The distributional bounds are given in terms of Wasserstein norms, and the pathwise bounds are given in terms of the probability of being safe, right? So if it's the paths are, so delta denotes the probability of being safe, so you want a smaller delta. So the distributional guarantees, if we look here, the distributional, the Wasserstein norms are guaranteed to have these bounds, rho and rho bar, that depend upon the Wasserstein distance between the initial distributions. They are bounded away from zero due to the unmatched uncertainties, independence of the driving Brownian motions, and these bounds are proportional to the filter bandwidth and the sampling rate. So this is similar to L1 deterministic performance bound, but we have the square roots here, and that comes because of the quadratic variation of the Brownian motion. So our bounds get even refined, which is natural because in deterministic case, you are very conservative with small gain and Lyapunov. In stochastic case, because of the stochasticity, you should be able to improve these bounds, right? Because now you get only probabilistic guarantees. In the absence of diffusion, when we're back to the deterministic systems, we recover the performance bounds of L1 adaptive controller for deterministic systems. Now, if we look into the pathwise bounds, right? So the pathwise uniform ultimate guarantees. So K delta and K hat delta, it's proportional to the initial norm of the distance between the initial distributions. They are proportional to filter bandwidth and the sampling period. And delta is the probability of deviation between solutions. So what we get basically a polylog dependence here, which is much finer bound than it's non-conservative and usable for very high assurance with very small delta. That's the, as we said, the safety violation probability delta that we want to be small. In contrast, the controllers with guarantees up to the order 2 mean and covariance, for example, in the literature, will have bounds of this nature without the log term. And to experience the difference, here is the difference when the log bound just becomes more useful for the planning purposes. So what we are proving here are the Wasserstein bounds for the L1 adaptive controller in the sense of distributions and in the case of this pathwise deviation. And we want these bounds to be useful for planners. So imagine how useful can be the bound given by the blue term versus the bound by the red, right? So this is a finer bound that the planner can use for planning less conservatively. While the other bound quite often is just not useful and people just keep playing with simulations to get the results. So here is the angular rate dynamics of a quadrotor, and you see, so we project here this tracking of the Wasserstein bounds on the left and right. So this is when L1 adaptive controller is on, and here is when it's off, and yellow is the nominal. So as you see, the nominal is a nice Gaussian, while the green is tracking it, bringing it to coincide with the Gaussian. And here is like more visualized in terms of distributions. As we said, the bound remains bounded away from zero. This is due to the independence of the Brownian motions that are driving the true system and the nominal system, with respect to which we compute these bounds. So the noise of the real world is there keeping us away from zero. So if we revisit the autonomy pipeline, we use basically L1 distributionally robust adaptive controller as the low-level controller within the pipeline. It's enabled by the guaranteed uniform distributional bounds in Wasserstein sets. And next, we developed the distributionally robust feedback motion planners. This is a CDC paper. It will be presented in Brazil. So what we do, we use the bounds of L1 adaptive controller for the planner. This is what we said is our aim. That's why the proof takes 4 years to get a bound that can be useful. So if we look into the stochastic optimal control literature for designing the planners, it cannot be applied to true uncertain systems due to the unquantifiable divergence. An alternative is to use distributionally robust stochastic optimal controllers, and the literature is rich on it. It gives you min-max optimal control over the ambiguity set of distributions, hedging against the effects of worse distributions in the ambiguity set, and generalization of the standard min-max optimal control problem is what's being solved in this literature. So we get tractable solutions via distributionally robust optimization, and there are plenty of papers in the literature doing that. So what does the planner require? So the planner requires the existence of an ambiguity set such that the true distribution will remain within it around the nominal distribution. Ambiguity sets can be determined under some scenarios. Availability of sufficient samples from true distributions. This is what's common in the literature. In our case, no, we do not say availability of sufficient samples from true distributions. We use just one sample xt from the true distribution. That's your feedback. That's at the current point. Our controller is deterministic. The guarantees are in the space of distributions. So we don't have this assumption. So again, the literature assumes known bounds for the moments of xt. We only assume finiteness of the second moment via well-posedness. And again, what we see in the literature, the state distribution is compactly supported over known sets. In our case, it's allowed to be unbounded. Our approach, we use the uniform guarantees provided by L1 distributional robust adaptive controller, and bidirectional communication between the planner and the controller is facilitated by L1's communication of uniform bound to the planner. And the planner can use it to generate the ambiguity set, the guarantee for the ambiguity set. And the performance guarantees are enabled by bidirectional communication. We get guaranteed distributionally robust planning and control of uncertain processes. Our approach is planner agnostic. So the initial investigation we did for L1 distributionally robust covariance steering, that's in CDC. So the high-level planner is a covariance steering controller. It has nominal plans for the first 2 moments of the stochastic system, and our approach will enable safe control of uncertain nonlinear processes with guaranteed margins on state distributions and high probability constraint satisfaction, for example, obstacle avoidance. Let's see what happens. Here are some numerical experiments. So we have a safe navigation of a 4D system. It's a double integrator here. True system is perturbed by unknown nonlinear drift term and diffusion. And the covariance steering here is how it works. So as you see here, the yellow is the nominal. When the uncertainty is wrapped around it, the blue, it starts colliding with the obstacles. And as we put the L1 adaptive controller, it would find the path because it will communicate the bound, what L1 can do, where it's safe, and the covariance steering will steer it correctly through the safe passage, right? So this is what we are achieving with the help of L1. What you see on the left and right, again, it's the tracking of the nominal distribution, which is the yellow, which is the Gaussian, and the green is the true system, which is not a perfect Gaussian, but it tracks and achieves it. So some of the ongoing and future directions, predictable and certifiable data-driven control. So we have a decoupled framework where we safety decouple from performance. Safety is important for planning and control. It has to be online. It has to be persistent. Performance is driven by the data, right? So data-driven learning can improve the performance. It can be done offline and opportunistically online. But it's important to have safety always guaranteed, regardless of the performance of the learning. So the learning can be intermittent, kind of, in some sense, from the perspective of online processes. So what we said in the beginning that we want to bridge the two worlds. So we have distributionally robust planning and control with L1 adaptive control architecture, and we have data-driven learning, and now they speak the same language. And the bounds from distributionally robust L1 adaptive control can be used by the learning algorithm, and it can be efficiently used for planning purposes and for other types of challenges like in vision systems and other type of ML applications. So we have no constraints on learning. We raise the abstractions of robustness, and here is kind of the framework. If we present it on a high level, we have learning and planning, and they both work with each other in sync. So the next step is to include perception and other high-dimensional sensing by high probability finite sample guarantees of Wasserstein metrics. We have to get also local high probability results to make it very useful for robotics applications. The current results are of global nature for now. We have fast and safe planning and reachability analysis of uncertain stochastic systems on our roadmap to be developed that will be enabled by L1 distributional robust adaptive controls, uniform distributional bounds, and tight high probability tracking guarantees, coupling with state-of-the-art high probability planners for nominal nonlinear stochastic systems. We're now working with Nick Matney, with Giole on an AIAA SciTech paper where we will use the TASIL algorithm. And further investigation into sampling-based stochastic optimal control algorithm, we have a variety of methods here to be explored. We can extend L1 to sample data systems to enable broader class of systems and continue development of novel approaches suited to the contemporary requirements of high-performing data-driven subsystems consolidated in a large system, guided by generalization, regardless of complexity of systems and solutions. Removing complexity should always lead to existing sound results. This is what we have signed under, that when all this stochasticity goes away, nonlinearity goes away, everything, we're back to gain and phase margins that people can understand. And this is what helps us to talk with industry, because when we present these results, it looks complex on the other side. But then we say, okay, take out diffusion, take out this, that, we are back to gain and phase margins. See, all these bounds naturally collapse. And this just kind of helped us to move forward always, that during this generalization, we watch out for these principles. And it can present a new perspective for certification authorities, because that links back all the way to known gain and phase margins used in contemporary regulations. That would be a path forward to verifiable adoption of autonomy for safety critical systems. I want to acknowledge our lab and students, people who do all this work. In particularly, all these developments were led by Aditya, who is our research scientist leading the group. He has been with me 8 years, spent the past 4 years on a single paper without doing anything else. And we have students like Sambu, who has been very helpful for him in these developments, and many others who work on different dimensions of the work in our group, although I did not get a chance to present anything else in this hour. And I would like to acknowledge all our sponsors from NSF, Air Force, NASA, everyone from industries, test pilot school, people who have helped, supported, shared ideas, provided feedback. With that, I can move to your questions. I believe I have maybe a few minutes for questions, right? Thank you so much.
Fantastic talk, Naira. And yes, indeed, we can open the stage for questions. We are a bit over time, but I think people here don't mind because it was very interesting. So let's open the stage for questions. You can either raise your hand and I give you the word, or if you want, you can also type in the chat and I will read for you. Let's see if there is anybody who wants to break the ice.
And they can send the questions by email as well if they are rushing to class.
Yes. Okay, maybe I'll break the ice myself. So fantastic evolution. I think you show how to take some ideas from architectures that you developed a few years ago and now made them actual with the current data-driven techniques. A question I'm curious about, and actually we discussed a bit sometime, is this is a lot about decision making. What about when you want to, how can you embed these architectures into design principles for the systems themselves, right? You zoom out even further and you say, now I want I know how to do decision making if you give me a system, but what's the system I have to design, right? For instance, a fleet of drones or these kind of things. Are you
Yeah, this
thinking
is where
about
we
these
have to
problems?
collaborate.
That's where we have to collaborate, right? But
All right, this is where we have to collaborate. And for example, the current paper that's due in December for the AIAA SciTech conference in January, we have kind of this tacile algorithm coming from Nick Madney's lab. We are now we are in the process of actually integrating it with the L1 bounds now. And we will be reaching out to all of you, all the co-authors on that paper, to show how this integration happens and how it can be used, for example, for optimizing the planner or even going through your compositionality analysis to make sure these bounds can be used for designing the system. Because the systems are so different in every case. If you go from airplane to self-driving car or to underwater vehicles, the challenges even change, right? For airplanes, stability comes first, and then only the performance, the planner, and other issues. You have to be first stable, not to crash. For self-driving cars, it's the planning challenges. So the systems are different in every case. I guess generalizing something too much has the danger of losing good performance in specific cases. When you are too general, in very specific cases, your performance will be very conservative and not suited to the context. But if you understand the context and you tailor it to kind of specific application, so there is always this sweet spot, how much you want to be general and how much you want to be good for that particular application, right? How much you borrow from the generality, how much you already go and say, okay, enough scaling this much. Let me be now non-scalable and be good here. Right? It's a sweet spot always to decide where to scale and where to kind of deliver on the.
Indeed. There a lot of work to be done there, but I look forward to working together.
And it's very exciting, and I look forward really to getting some work done together and maybe pushing some proposals out and going through some exciting demos. It's always exciting when your student is on the airplane flying his controller.
Yes, that's very cool.
So we have
any other question for Naira? I think some people left because of the hour, but I want to give the chance to the few that remained. Don't be shy.
They will email.
Yeah, I think that's the best thing. Maybe email Naira with some questions. I'm sure as soon as we put this online, it will attract a lot of attention. So thanks again, Naira, for.
Thank you, Giovanni. Thank you for having me, and we'll send the paper soon. Okay.
Absolutely.